Okay, so I'm going to talk about my recent work on the Azimuthal angular symmetry of soft gluons in jet production. This is a paper that I wrote with Bo and Shao, who gave a seminar in your group a few weeks ago, and Feng Yue and Jiang Zhou. And I have to admit that my collaborators are much more expert than I, but I speak from my perspective. So here's the, it doesn't go to the, okay, so here's the contents of my talk. So I first give you a motivation, basically the ESC and the multidimensional pattern distribution functions, or in other words, the tomography. And I will explain how the jet angular correlation helps understand these higher dimensional new pattern distribution functions, especially the TMD. And then we point out the necessity to do the resummation. So this is going to be an angular dependent resummation, and explain how we're going to do that and calculate various observable involving jets angular correlation. And my last part of my talk, I will focus on the so-called linearly polarized Gluon distribution function and associated angular distributions. So in order to motivate you, let me start with some future experimental proposals. So this table shows 3 experimental projects in the future. Of course, there is this ESC, the electron ion collider in Brookhaven, in the US. And there is a proposal for another ESC, the Chinese version of the ESC, in which was both of them are probably, I think this timeline is a bit optimistic, but I hope the US is going to happen, and I hope the same thing happen in China. And there are also proposals to do the electron and proton scattering at the LHC, and there are several possibilities, but this was much less uncertain, but I hope there will be something. But so all this implies is that we are entering the era of precision electroweak and perturbative QCD, and the precision study of nucleon and nuclear structure in the next 20 to 30 years, at least until the day I retire. So that motivated me to work on the ESC physics. So here's the most important scientific goals of the ESC as articulated in the white paper, and also the National Academy of Science report, and also the yellow report, which was published 1 year ago. And so there are 4 pillars. One is the origin of nuclear mass, the origin of nucleon spin, and gluon saturation at small x, and the nucleon tomography. And I'm mostly talking about this last bullet, the nucleon tomography. So what do I mean by tomography? So this is basically a generalization of the ordinary pattern distribution function. So here's the definition of a PDF of, let's say, the up clock distribution function. And from our viewpoint, this is a one-dimensional tomography in the sense that it depends only on one variable, which is the longitudinal momentum fraction x. And however, you can generalize the notion of PDF by including more degrees of freedom, and by considering that pattern in the nucleon has also have a transverse momentum k perp, the 2-dimensional vector, and also they are spread in impact parameter space b perp. So you can generalize PDF such that they include this dependence on this additional degrees of freedom. So once you add this k perp dependence, then this is called the transverse momentum dependent distribution, TMD. This is a 3-dimensional tomographic picture of the nucleons. And once you include the b perp dependence, then this is called the generalized pattern distribution. This is the 3-dimensional tomography. And if you include both b perp and the k perp dependencies, then this is called the Wigner distribution function. And that's a 5-dimensional tomography. It's a complete picture of the nucleon as one pattern distribution function. So here's a kind of family tree of PDF. So you have a mother distribution function, the Wigner distribution function at the top, and by successively integrating over b perp and k perp, then you can generate all the lower dimensional pattern distribution functions, TMD and GPD and PDF. form factors. And in practice, instead of working with Wigner distribution function, it's more convenient to work with the so-called GTMD, which is a Fourier transform of the Wigner distribution function. So instead of B perp, you do the Fourier transform to the delta perp, which is the momentum transfer. And this is what appears in the observables. So, all right, so, but in fact, this family tree is not yet complete because once we consider the TMD and GPD, you find new kind of distribution which has no analog in PDF. And one of such example is the so-called linearly polarized Gluon distribution function. So this is a Gluon TMD defined in the usual way, except that you have open indices I and J in the transverse plane. And we have two pieces. One is this proportional to delta Ij, and that is ordinary unpolarized Gluon TMD. But there is an additional term which has this tensor structure. And this is called linearly polarized Gluon distribution function. And the physical meaning of that is you can see it by looking at the tensor structure. So this tensor structure, 2ki kj minus delta ij, you can write it as interference between the positive Gluon helicity and negative Gluon helicity. So the diagram is like this. So you have a positive helicity Gluon in amplitude, and you have negative helicity Gluon in the complex conjugate amplitude. So this is an entirely new structure, which appears only if you consider the TMD. And once we integrate over K-pop, this term simply vanishes by symmetry. So we are dealing with a new kind of TMDs, which has no analog of PDF. And there has been a proposal that this function can be measured in experiments. So if you consider the DIS, for example, and measure the final states, which consists of jet and 2 or the heavy quark pairs, and if you look at the cosine 2 phi correlation function between the K1 and K2. So let me define this capital P, which is a relative momentum, which is very hard. So P pub is very large. So the two jets are almost back to back in the transverse plane. And we also define this Q perp, which is the sum or the vector sum of K1 and K2. So if you look at the situation that P perp is much larger than Q perp, then you find that the cross section depends on the cosine 2 phi, where phi is the difference between these two vectors. And this is caused by such a cosine 2 phi dependence can be generated by this linearly polarized Gluon distribution. So if the experiments can measure this cosine 2 phi, then that could be an experiment signature of the linearly polarized Gluon distribution function. So there has been a similar proposal of this kind. Now also, I want to talk about this Wigner distribution. And as I said, this function depends on both on the B perp and K perp. And you can think of various types of angular correlations. So there is, of course, this unpolarized, the angular independent term, W0, and probably the leading angular dependence, the strongest angular dependence, is the so-called cosine elliptic Wigner distribution function, which has a characteristic cosine 2 phi dependence, where the phi is the different the angle between B perp and K perp. And there is another, so probably this is the most strongest angular dependence. And there is another dependence on the cosine phi dependence, and this is called the spin dependent orderon. And this term exists if the proton is transversely polarized. And if the proton is longitudinally polarized, then there is another type of angular correlation, and this is proportional to the sine phi. And this is related to the orbital angular momentum of quarks and gluons. So, so this is a Wigner distribution function, and if you go to the Fourier space by Fourier transform from B to delta perp, then you get the GTMD, and you have a corresponding cosine 2 phi and cosine phi and sine phi dependence, where phi is now the angle between the delta and K perp. The interesting question is whether we can measure this angular dependence in the experiment. So we propose such a measurement. So this is a proposal to measure this elliptic cosine 2 phi part of the Wigner distribution function, which in this paper with the Bergen and Fenn in 2016. So what we propose is to measure the dijet event. It's an exclusive dijet event where the proton scatters elastically, and you measure two jets in the forward direction, so jet 1 and jet 2, and define the capital P and capital small q as usual. So capital P is the difference between K1 and K2, which is large, and Q perp is the sum of the K1 and K2. And I also define the delta, which is a momentum transfer of the proton, since proton scatters elastically. Now one can show that to leading order in the small x kinematics, this cross-section differential in delta perp and Q perp is written like this, and this S is the GTMD. It's a Gluon GTMD. And if you are familiar with the small x Calaglas type of physics, then this is also known why this is actually proportional to the so-called dipole S matrix in the context of small x physics. And since this GTMD contains the angular dependent term, which is governed by the selective part of the Wigner distribution function, then you find that this cross-section has a characteristic angular dependence between capital P and delta here. And if the experiment can measure this cosine 2 phi dependence, and this is a signal of the elliptic Wigner distribution function. Now, one can also do the same thing, actually not in DIS, but also in heavy ion collision or PA and PAA collision, if you consider the so-called ultra peripheral collision. So this is a process where the nucleus, so there's a heavy nucleus like in RHC, acts as a source of on-shell photons, the Weizsäcker-Williams photons. And so there's a real photon instead of virtual photon in DIS coming into the proton, and there's the final state. It consists again of two jets in the forward direction. And the good thing about this is that the cross-section is enhanced by Z square, where Z is atomic number of the nucleus. So if this is a gold nucleus, then Z square is like 6,000. So this is a very large enhancement of the cross-section. And so if you write down the cross-section, then you have this photon flux factor, this dn d omega, which is calculable in QED. And this one is proportional to Z squared. And there is a QCD part, which I call the A square and AB term. And so this A and B, if the experiment can measure this A and B, then from that one can actually reconstruct the angular independent and angular dependent part of the GTMD. You can actually do it analytically. Well, actually, in principle, there's analytical. You can do this inversion analytically, even though you have this complicated convolution in momentum space. In the case of if the photon is massless, as in UPC, you can actually invert this formula analytically and extract the angular independent and dependent parts. So this has been proposed. And here's some numerical estimate of this cosine 2 phi effect, which was done by my colleagues in Brookhaven. And this is based on the calculation by the so-called solution, based on the solution of the Jim-Walk equation with the B dependence. And it's important to solve the Jim-Walk equation with B dependence, the impact parameter dependence, because we are talking about the Wigner distribution function, the GTMD. And this is nowadays possible, and this has been done. And so the left-hand side is cross-section, and the right-hand side is the coefficient of the cosine 2 phi, which is V2. This is very similar to the elliptic flow in heavy ion collision. And you can see this is only, it's a very small effect. It's only 1 or 2% effect. But if the measurement is precise enough, then maybe this is measurable in future. All right, so another aspect of the Wigner distribution function, as I said, is the connection to the orbital angular momentum. So this is the so-called Jaffe-Manhar decomposition, where the proton spin 1/2 is decomposed into the various components. So there's delta sigma, this is the quark helicity components contribution to the nucleon spin, and there is a delta G, that is a Gluon helicity contribution, and there are canonical orbital angular momentum from quark and gluons, LQ and LG. And it has been shown that this LQ and LG can be defined through the correct definition in QCD of this LQ and LG is through the Wigner distribution function. So this is a B cross K. It's a classic definition of the angular momentum, orbital angular momentum, weighted by this Wigner distribution function. And this is a correct definition of the Wigner. This is a gauge invariant proper definition of the orbital angular momentum. And one can also define the, yes.
So it's a very basic lecture thing in quantum mechanics when you're interested in the interaction or like possible Hamiltonian, like interaction between a system, like in a system, and then by assuming different symmetries, then you can say that a different level, like the, I don't know, spin interaction or angular momentum interaction, what kind of form the Hamiltonian can it have, and then you can parameterize those with functions, and experimentally by doing I don't know, like scatterings of atoms, you can figure out some part of this Hamiltonian. And is it something similar here that you're saying that the proton has this angular momentum or spin or whatever, and based on that you can assume different form of this Wigner distribution, or how do you get this these terms?
Yes, so you have this in QCD. You have the angular momentum tensor, which is a conserved current associated with the Lorentz symmetry, and from so this describes the angular momentum of the system, and you have an operator definition of that in QCD quarks and gluons. Then you can do this decomposition, starting from this operator decomposition in a gauge invariant way. So you have rigorous gauge invariant definitions of all the four components. So you start with the angular momentum tensor operator, and you can decompose this rigorously in gauge invariant way. Does it answer your question?
It did. Thank you.
Okay. Yes. So in this way, the proton. So these four entries are proton matrix element of the four gauge invariant operators. Yes. Right. So yeah. So there's been lots of effort to measure each of these components. So delta sigma has been measured in the last 30 years, and delta G has been measured in the last 20 years. But there have been no measurements so far whatsoever of this LQ and LG, the orbital angular momentum. So to understand this part, you need to understand the Wigner distribution function. The measurement is very difficult because it is related to the Wigner distribution function. So the measurement of OAM is equivalent to the measurement of the Wigner distribution function. And very recently, this is my most recent paper, we proposed a new observable for this OAM for the Gluon orbital angular momentum. This is basically, we showed in this paper that if you measure the double spin asymmetry in diffractive dijet production, yes, again, you have two jets in the final state, and both the proton and electrons are polarized in the longitudinal directions. And if you measure this double spin asymmetry, then one can show that the cross section is a convolution, is a product of the so-called Compton form factor for the unpolarized GPD, and there's another piece which is proportional to the orbital angular momentum. So I think, so there's been several proposals before, but I think this is the best, most promising observable to measure the orbital angular momentum. Anyway, this is just advertisement, and this is again related to the angular correlation in the dijet measurements. All right, so we have made several proposals, and kind of motivated the experimentalists at GMS, and so they actually measured what we proposed. So they used the ultra peripheral collision at LHC, And so they may actually measure the dijet correlation. So what they did is the following. So they measured, so the nucleus, the Chi emits a real photon, and this photon eventually materializes in the two jets in the power direction. And they measure the Q perp, which is the sum of K1 and K2, as a proxy of delta. So remember, original proposal is to measure the correlation between between the capital P and delta. But instead of delta, they measure the Q, okay? Because to leading order, delta perp is simply the negative minus Q perp, right? It's just a recall momentum. So by momentum conservation to leading order, Q perp is simply the minus delta perp. So they measure the Q perp, and they measure the correlation between Q perp and capital P perp, okay? And this is supposedly a signal of the elliptic part of the Wigner distribution function, but there was a surprise. So this is the data on the right-hand side, and you see the cosine 2 phi is like 20%, or depends on the jet total momentum Q perp, but it's like 20% or even more, even like 40% or something like that. But we originally proposed that this prediction, the theory prediction, is like 1 or 2%. But what they measured, which is supposedly measured the elliptic Wigner distribution function, is actually 40%. And then this was actually the motivation of this collaboration. So we are puzzled by that initially, and we figured out. So the conclusion is that this has nothing to do with the Wigner distribution function, and it actually originates from the perturbative QCD radiation. So let me try to explain that. So here's some general consideration. So as I said, to leading order, the total dijet momentum, Q perp, is simply the minus of the proton recoil momentum, right? So d sigma dq is simply equal to the d sigma d delta. However, we have soft Gluon radiation, like kg perp. There may be many radiation like that. So Q perp is minus delta up to some soft Gluon transverse momentum, right? And because of the collinear enhancement in QCD, the soft Gluon momentum K perp, Kg, tends to be aligned jet direction. And since Q perp is the minus of Kg, and this also means that the Q perp tends to be aligned along the jet direction, because jets are just back to back, and soft Gluon is emitted along the jet, so the recoil momentum is also along the jet direction. So you have to take this into account. So the actual measurement, what is measured in the experiment, d sigma dq perp, is actually a convolution between the primordial Q perp distribution Q perp prime times some soft factor. And you have to calculate this soft factor in perturbative QCD by doing a resummation. And that's basically what we have to do now. So here's the one loop consideration. So let's just emit just one Gluon, the soft Gluon. So and calculate this soft factor S, right? So the to 0th order, this is just a delta function, just by momentum. Yes, so there's no emission. And if you do the one Gluon emission, then you have this familiar soft Gluon emission kernel. And so you have to integrate over the phase space of the soft Gluons, excluding this jet cone. So you have to integrate outside this jet cone, and you have to do this integration. And this integral depends on the angle between P perp and Q perp. So we did that. And this is actually the most mathematical, technically difficult part to carry out this integration. And you can imagine that you have to avoid this. You have to integrate over this white region, excluding this jet cone region. And somehow we managed to do it analytically. Well, actually, we're working with Bergen, and he's a genius doing this kind of integration. So this is a complete analytical result. And so yes, so this A0 and you see this log of R. This is a kind of regularizes the collinear divergences, but you still have a soft divergences. You can see this is 1 over Q perp squared. And this is a soft divergence. There's no collinear divergence because of the jet cone. So there's an angular independent term and there is a cosine 2 phi term, and there is also a higher order cosine 4 phi, 6 phi, and so on. And so if you integrate over this cross section over Q perp, then you actually find that the angular dependent part is divergent, because you have 1 over Q perp, and there is no compensate, there is no plus prescription. So if you integrate, this is so there is a big difference between the angular independent and dependent terms, because the independent term, there is a virtual correction which converts this 1 over Q square into the plus this prescription. So if you go to the B space, the momentum space, and the coordinate space to do the resummation, then you get finite result. So the original, so this infrared singularity is regularized by the plus prescription. And this is a well-known Sudakov factor, so you can do the resummation by simply doing the exponentiation of that. However,
Yoshi?
Yes. Yeah.
So the reason for the reason for this is that the virtual term is just the integral over the angle, right? So all the higher order terms are just integrate out to 0.
Yes. So the virtual term doesn't care about the angle.
Yeah.
Right? Yeah. Because you just integrate about the phase order. Yes. Yes. So so there is no plus prescription for the virtual term. However, if you do the Fourier transform, then you get completely finite result. You just get 1/2. It's just a number. So if you go to the B space, the coordinate space to do the resummation, if you do the, okay, so I didn't say that. If you do the TMD, if you want to do the TMD resummation, you go to the B space, the Fourier transform. And this angular dependent term is actually singular in the momentum space, but if you go to the coordinate space, you get something completely finite. However, if you go to, so this is just one loop, but if you go to the higher orders, then there are also logarithms. You actually get logarithms even for the angular dependent term in the B space, but actually the pattern of this logarithm is the same as for the angular independent part. So the one can actually do the resummation by using the same Sudakov factor. This has been shown by Katani and his collaborators. So then you can do this resummation in the B space and then Fourier transform back to the Q space and get the Q perp distribution like this. So something remarkable happens here. So the original one loop result you have in momentum space in fixed order perturbation theory, you have this 1 over Q perp squared. This is a singular distribution function. It's not integrable, but if you do this, go to the B space and do the resummation, then first Fourier transform back, then you get completely finite result. The average of cosine and phi is proportional to the Q pi to the power of n. So the original distribution in fixed order perturbation theory is divergent, but after the resummation, you get something completely drastically different, which is finite. And this is why the Katani put this very suggestive title that the infrared safe but divergent for this angular dependent resummations. So
yes. Sorry, this term is looks very UV divergent now. Is that, or is it just like the soft?
Oh no. This is just a soft. This is after the soft approximation. So so it should be fine. All right. So we played with some numerics and tried to explain the CMS data. And so we took the LHC kinematics. Jet momentum is 35 GeV, and we measured, we calculated the resummed cosine 2 phi as a function of jet total momentum. So Q perp is much smaller than P perp. In this kinematics, we need to do the Sudakov resummation, and we get this flat behavior, which is order of 15%, which is kind of similar to what was observed in experiments. This was the experimental result is slightly higher, like 20%, and it's an increasing, monotonically increasing function of Q perp. And for that, to explain that, we also included some certain kind of power corrections, and we managed to find increasing behavior as a function of Q perp. Well, this is not a complete calculation because we only included a part of the power correction. And by power correction, I mean this coefficient of cosine 2 phi has a power correction of 1/q pub. And once you include this term, then you can mimic the experimental tendency. All right, so this is what's the bottom line? So we can actually learn a lesson from here. So CMS measure the Q pub dependence as a proxy for the delta pub, but they are not the same thing, right? So because Q pub is very much sensitive to the QCD radiation corrections, and this will affect the cosine 2 phi dependence. So delta to really measure this elliptic part of the Wigner distribution function. So that's the lesson we find. So Q pub cannot be a proxy for delta pub. That's the conclusion. All right, so this is for the exclusive dijet production, and here we considered several applications, related processes, and let me show you 4 of them. And the first one is lepton-jet correlation in DIS. So this is a lab frame in DIS. The electron and proton are collinear to each other in this lab frame, and we measure the correlation between the electron, scattered electron, and the jet. And the difference from the previous case is that there is a quark in the initial state. And so in this previous example, you have a Pomeron exchange in the T channel. So the T channel object is color singlet. So there is no radiation from the initial state, but in this example, there is an initial radiation from the initial incoming quark.
Yoshi,
yes.
In the previous case, you didn't mention, but don't you have a process dependence? Like depending on what channel was the interaction with the proton and the photon or the quark, like the non-global things that you resum should depend on that, shouldn't it?
Well, in this so this is a high energy small x kinematics. So to fast approximation, what's exchanged in the T channel is Pomeron. So there is no. So you have a radiation only from the final state quarks pairs that we resummed.
But the Pomeron that can come from any quarks or any gluons inside the proton, right? Or
well, the Pomeron is a color singlet, 2 gluon bound states, let's say. So there is no radiation from that. The only radiation we have to care is the radiation from the QQ budgets. And then of course you have to include the non-global log, but we haven't done that. Okay. We actually included a non-global log in my previous paper in 2019, shown here. And in this paper we included the non-global log, but we didn't include we are not very careful about angular dependence. And in this successive paper we included angular dependence, but we didn't include the non-global log. And it's very difficult to include both. We haven't done that yet.
Okay.
All right. So yes. So this is an exclusive dijet, and here's the lepton-jet correlation. And difference from the previous case is that now there is a radiation from the incoming quark, and because of that we have a double log. So you see this 1/q square times log of q square. Because of the radiation from the incoming quark, you have a collinear radiation as well. And so you have the leading term is a double log, and you have also a single log. And there is a cosine phi term because there is only one jet in the final state. So you break the symmetry. So you have 2 phi cosine 3 phi and so on. And we can do this resummation in the B space. So you have in the B space, you have this double log of Q perp, capital Q times B perp squared that can be resummed. And in this case, you get a Sudakov factor like that in the B space, and then Fourier transform back to the momentum space. And we can show that this cosine. So here's the resummed results for the cosine phi, the cosine 2 phi, and the cosine 3 phi. Angular modulation, and you can see this this cosine n phi is proportional to Q perp to the power of n. You can see this tendency. So again, I want to emphasize that the distribution is singular in the fixed order perturbation theory, 1/q perp, but after the resummation, it gets completely finite without at the origin. And my second example is the photon-jet in proton-proton scattering. So this is, you have the final state contains the back-to-back jet and photon, the real photon, and the leading channel is the quark gluon scattering channel. So in this example, there are actually three colored patterns in this 2-to-2 scattering. So there are two quarks and one gluons, and they all radiate. So we have to consider the soft gluon radiation from these three pattern systems. And you can actually decompose the soft emission from this three-part system by considering quark jet. So you can decompose this system into three dipoles. One consisting of quark jet, quark and jet, and quark and gluon jet dipoles. So you can decompose this system into three sets of dipoles, and you can calculate the soft radiation from each of them, and then you just add up. So here we calculated this angle, the Cn, the coefficient of cosine and phi, and we did the resummation in this case. So we can also do this resummation in this situation where we have three patterns. And the most complicated case is the case where you have four patterns. And so this is an inclusive dijet in proton-proton scattering. So the dominant channel is gluon scattering into two jets, the back-to-back jets. And in this case, you have to be worried about emission from all the four patterns involved, both in the initial state and the final state. So you can imagine this is the most complicated example, but we somehow managed to do that. We calculated the coefficient of the cosine to phi, which has this very complicated structure in the kinematical Mandelstam variable here. So we have also the angular independent term and angular dependent terms. And you have a double log because you have gluons in the initial states, right? So the resummation is actually complicated if you want to try to do it in full, but if you only focus on the double log contribution, then you can, it's simple because this double log term is universal and it's actually diagonal in color space. But if you go to the subleading terms, the single log resummation, then you have to do this resummation in the matrix form in color space, because in 2-to-2 scattering, if all the patterns are colored, then you have various type of color representation exchange in the T channel. So one gluon emission can change the color structure. So you have to do the resummation in the matrix form in the color space in a different representation. And we haven't done that. And we only did the leading double log term, which is universal and independent of the color basis. Yeah. But in principle, you can also do the subleading single log resummation. And this is, if you're interested, then you can look at the paper by Katani and his collaborators for the basic approach. All right, my last example is it's a bit different. It's not QCD, but in QED, you can actually think about the similar kind of resummation also in QED, in the pure QED context, because you have soft photon emission. So here's so there's been lots of interest in the ultra peripheral collision in LHC and LUIC, where you produce back-to-back lepton pairs from the ultra peripheral collision. So you have two photons from two nucleus annihilate and produce a muon pair in the case of LHC and the electron pair in the case of WIC. And this has been measured, the angular correlation between these two electron, two muons have been measured. And again, this if you measure the correlation between capital P and small q, then you have to worry about the soft photon radiation in this case. And you can do the similar kind of summation. Of course, we don't have jets here, and we don't have just electron, but in this case, the mass of the electron acts like the collinear cutoff. So the jet cone radius r is in this case the role of r is played by the electron mass or the muon mass divided by k-perp, and this acts like infrared cutoff. And you can do this calculation with this coefficient of cosine 2 phi. You can do it analytically, and you find that the coefficient of cosine 2 phi is almost the same as the coefficient of angular independent term. So you would expect a very large symmetry. And so you can see this is the numerical result, the cosine 2 phi, and you can see this is very large, like 60% or the 70%, depending on the Q-perp. And, and we're actually talking about a very low PT, like 100 MeV, this kind of measurement. From there, the soft photon resummation is crucial to get this. There was a previous work by Klein and Bowen and Fenn, but we have revisited their calculation, and this is actually an improved calculation compared to their previous approach. All right, so let me come to the how much time do I have? Oh, that's 10 minutes. Yes. So let me come to the last part of my talk. It's so I want to focus on the so I want to focus on the linearly polarized Gluon distribution function. My last part. So as I already explained, there's been a proposal to measure this linearly polarized Gluon distribution function by measuring the dijet correlation in DIS, or the heavy quark pair production in pre-P, and also the Higgs boson production in LHC. And the idea is that if you measure the cosine 2 phi correlation between the two jets, K1 and K2, or capital P and Q, then you have an angular dependent term, and this is proportional to the linearly polarized Gluon distribution function, H-perp. This could be the experimental evidence of this H-perp function. However, there is a caveat here, because as I've been saying, soft Gluon radiation from the final state jets, and also from the initial incoming Gluon, this can affect the cosine 2 phi. So you have to take care of that. And also, another problem is that you can actually generate linearly polarized Gluon distribution function purely from perturbation theory. And this can be perturbatively generated. I will explain that in the next slide. So in fact, these two effects has never been quantitatively studied in the literature, and that's what we are going to do. So let me explain how to generate this linearly polarized gluon. So let's think about this very basic one gluon emission. It's a derivation of the Dirac splitting function. Okay, so the quark splits into the gluon and quarks, and gluon has a momentum function z. And usually you sum over this Lorentz index I and j in the amplitude and complex conjugate amplitude, right? But if you don't sum over this I and j, then the result that you get is the following. So you have delta ij, whose coefficient is this familiar splitting function, but there is additional term which has exactly how this the structure of this linearly polarized gluon. And the reason for that is that this gluon, this emitted gluon, is polarized actually, because so the spin of this gluon can be both plus and minus, right? So in that sense, this emitted gluon is polarized, and you usually don't realize that because you sum over I and j. But if you don't do that, then you get this. And so it's crucial to have a transfer of momentum to perp to get this new structure, and this is how you can generate perturbatively the linearly polarized distribution function. So you have to consider that. So in some sense, this linearly polarized Gluon distribution function has two components. One is the intrinsic part people are trying to extract from an experiment, and this is the only piece that people have considered in the literature so far. And this is an perturbative function, so you have to model, and we use the model used by Daniel Bohr and his collaborator. So this is what we call the intrinsic part, which we are eventually interested in. But there is a background, which is perturbatively generated by this mechanism, and so that is proportional to the collinear PDF, and you can calculate this coefficient C using perturbation theory. So there are two components, and they have different dependencies on the B pub if you go to the B space. And that is sort of controlled by the photon virtuality, the scale, the renormalization scale. So you have the Q dependence, the scale dependence is completely dominated by the Sudakov factor, which is log of Q squared. So if you go to the Q squared, then B pub is small, and this is dominated by the perturbative part of the linearly polarized. But if you got a small Q squared, then you're sensitive to the large B, then you're sensitive to this non-perturbative, the intrinsic part of the linearly polarized. So depending on the value of Q, you have different contribution becomes dominant. And you can see if Q is 5 GeV or 100 GeV in the case of Higgs boson production, you can see the large Q square is completely dominated by the perturbatively generated linearly polarized. But if you go to the moderate Q, like 5 GeV, then you have a non-perturbative part is dominant. So by changing Q perp, you can dial the relative contribution from these two mechanisms. And on top of that, as I mentioned, we have to add the soft gluon radiation in the final stage. So in this case, where the incoming gluons can emit soft gluons, because this is an inclusive dijet production, it's not exclusive. So the incoming gluon, we only have one gluon, not two. So this gluon can emit. And then there is emission from the final state quark and anti-quark pairs. So we have to calculate the cosine 2 phi dependence of this soft gluon emission, then do the resummation and the Fourier transform back to the momentum space. And we did that. So we included these three contributions: the intrinsic linearly polarized term, and also the perturbatively generated linearly polarized, and then finally the soft gluon radiation. This all affects the cosine 2 phi. And here's the numerical result for the EIC kinematics. And you see this total contribution, the solid line, and this dotted dashed line is intrinsic, or this two component, the sum of the intrinsic and the perturbatively generated. And you can see that the cosine 2 phi is completely dominated by this final state gluon emission function. And this is the same both for the longitudinal photon and also the transversely polarized photon. So this is very, this makes the extraction of the intrinsic H plus quite challenging. And there are many papers written about this H pub dependence, but once you but you have to worry about this soft gluon radiation. It's quite, I would say it's quite challenging because you have a huge background here, which has nothing to do with the linearly polarized gluon distribution function. And one way to reduce this final state radiation is to go to larger R, because then you have a log of R, and that becomes small. So that's one way, but you still it's quite challenging. You need a very accurate control of this perturbatively generated cosine 2 phi dependence. So the extraction of linearly polarized gluon is not as simple and straightforward as previously thought in the literature. All right, so that brings me to conclusion. We talk about the multidimensional tomography and TMD and GPD and Wigner distribution function. This is an important theme of the ESC, and I show that some of the interesting tomography, like angular correlation between B and K, you can extract from the measurement of jet angular correlation. But by doing so, you have to take care of the soft Gluon radiation from the incoming and the final state patterns that can affect this intrinsic angular dependence from the non-trivial pattern distribution function. And in the case of exclusive dijet, then QPerp cannot be a proxy for delta, so you have to measure delta. That's the only way to go to really measure this Wigner distribution function, the intrinsic angular correlation of the Wigner. But in the case of inclusive dijet, like in this measurement of linearly polarized gluon, then soft Gluon effects are inescapable. You have to live with that. All right, so that's basically what I wanted to say. So thank you very much.
Great, thank you very much for this nice talk. Are there any questions?
I have a few questions.
Sure.
Maybe so you were saying that first of all, this most of your calculations were done in this kind of diffractive cases, right? Or elastic scattering, basically, somehow.
Yes, this is elastic on the proton side. Yes.
Mm-hmm. So I wanted to ask, do you use the small x physics here for something special, or is it providing you the model for the Pomeron, or how, I mean, how does the small x physics play a role here?
Yeah, this is a usual approach in the small x Calaglass type of calculation. So you have a dipolarized matrix, both, and the GTMD is simply proportional to the dipolarized matrix.
Okay.
So in some sense, we are reinterpreting the usual calculation in terms of GTMD. It's the same thing.
Right.
They're actually proportional, at least for the gluon. Okay. So we are not inventing any new. It's not a model of it's not a model of Pomeron. It's just a usual Calaglass type of calculation in the small x. Yes.
So in order to get the elastic one, you need to do the average on the level of amplitude. Is that correct?
Right. Yes. Sure.
So okay. So and what was the difference between this case and this inclusive production? So what do you?
Yeah. So inclusive production. Let's see. Yes, so in the inclusive case, you sum over the final state on the proton side, and what is exchanged in the T channel is just a single gluon which can radiate. Whereas in the exclusive case, you exchange Pomeron, which is color singlet, so there's no radiation from that. So that's a main difference. Yes, so
so this guy can radiate.
Yeah, so in the inclusive case, there's no delta. So that's